Good morning everyone, I am Mr. Ish. Thank you for joining me for this video. We're looking here at a video on the limit laws, and these laws by no means are difficult. It's more of a formalized topic, but inherent substance over here is actually easy. If C represents a constant and you have two functions f of x and g of x, each within which the behavior you can do x approaching a for each of those, and they both exist, then these are the following laws that are present. You have what is called a sum law. The sum law looks something like this. Limit as x approaches a, you have f of x plus g of x. This right here represents a sum. Then in this instance, based on the law, you can separate it into individual limits such that you will have something which will look like this. You can apply the limit individually to a sum. So how do you verbalize this? That the limit of a sum is equal to the sum of their individual limits, and that represents the sum law. Very close to that is what is called the difference law. And you know, with the difference law you have the minus sign which appears over here, and in this instance the difference law stated verbally is that the limit of a difference is equal to the individual difference of the two functions. So you can separate a function, a compound function, across its operating sign, which could be a positive or a minus, and then individually apply the limits accordingly. There is such a thing called a product law of limits, where if you apply a limit to a product of functions, you could separate it such that you can individually apply a limit to each of the substituents that are being multiplied. So that's a product law, that the limit of a product is equal to the individual limits of the items that are being multiplied. Then there is also the quotient law of limits, where if you apply a limit to a quotient, you could separate these substituents into their individual limits such that the limit of a quotient is equal to the individual limits of the items that are being divided, so long as this condition exists, that the limit as x approaches a, the denominator function, the g of x, it does not approach 0. So you don't want to be seeing this situation, because then you end up zeroing the denominator, which would not be permissible. So for the quotient law, generally in all instances this rule applies, that you can separate the substituents across a divide, but the denominator expression must not yield a 0 upon its limit calculation. For this limit, the constant multiple law, the law is such that if you have a function which is being applied by a constant, so you're doing a limit of this combination over here, the limit can be calculated such that the constant can be pushed outside, and then you can individually calculate the limit of the function you're looking at. And that would be the constant multiple law of limits, where the limit can be expressed such that the constant is pushed outside and it is evaluated at the end simply by multiplying it with the answer that you receive here. The answer that you get here, you multiply it with your constant, and that right there reflects the answer of this item over here which is being evaluated. So that's a constant multiple law of limit. So you have to be aware of the sum law, the difference law, the product law, quotient law, and then the constant multiple law. And these are all easy laws to understand because they're quite easy to comprehend and apply in terms of questions that you might see. So let's put these laws to work. We have a graph over here which represents two functions. We have a function f which is separated, as you can see. We have a g function which is a parabola with the vertex at 0, -2. Generally for these limit laws you have to establish that both right hand and left hand limits apply and they are equal to one another. In those instances where the limits on the right and the left hand are not equal to one another, you can only establish the limit laws as being one-sided versus two-sided. If the question over here was stating find limit as x approaches 2, you have 3 f of x. How would you go about answering this? Well, you know, since you only have an f of x established here in your question, you only look at the f function curve, which is this horizontal line. At x equals 2, you always have to look at both right hand and left hand limits. Here's my x coordinate here for 2, you have to look up over here. When you look up over here, you end up right over here, and then you see that as x approaches 2 from the left, you're looking at the values on the left, and as x approaches 2 from the right, you're looking at the right. You see that your function value here in terms of the y value or the output is a 4. So as limit as x approaches 2, you can clearly establish right hand and left hand limits, and they're both equal to each other, so a good limit exists, and that limit happens to be 4. But that's just the limit of x approaching 2 for f of x. When you have the constant multiple law here, you're essentially looking at everything as 3. times the limit as x approaches 2 f of x, and we've already established f of x here is a 4, and you do 3 times 4 and your answer for this question is a 12. Let's look at this next one. Again, these questions are not hard by any means. We have x approaching this a value of minus 2. We have this difference to evaluate with regards to this limit. You know, you could separate all of these out individually. Look as x approaching minus 2, you're looking at f of x, and then you're doing limit as x approaches minus 2, you're looking at g of x. You again have to establish that right hand and left hand limits exist over here, and we should do that and then come up with the final answer. When you look at the f of x function, which is these horizontal lines, as x approaches minus 2, here's my minus 2, you're looking down over here. When you're looking down here, you're looking across, you end up having a y value of, let's say, a minus 4, because that's what it is, y equals minus 4 over here. At this specific point, you can have both right hand and left hand limits exist, and they both happen to be minus 4 as x approaches minus 2. So we know that minus 4 represents the value for the limit of f of x, which is a minus 4. Now we have to look at the g of x. When you look at the g of x over here, which is this parabolic curve, you're looking right here, because that's as x approaching minus 2. When you're looking either from the left and you're looking either from the right, you have a continuous function over here, and you have both left hand and right hand limits equal to each other, and in terms of the output, you're seeing a value of 0 and a 0. So in both of these instances, x approaching minus 2 exists because you have minus 2 from the left and minus 2 from the right. Right hand and left hand limits are true. So what do you get here as the answer? Limit as x approaches minus 2 f of x, you have a minus 4. Limit as x approaches minus 2 for g of x, you have a 0, and your final answer ends up being minus 4, and that's a good answer for this question right here. Let's look at this next example, and again keep in mind nothing over here is drawn to scale. We have limit as x approaches 3, you have a product over here. The product of this limit as x approaches 3, you can use the product law and separate everything individually across their own limits. Limit as x approaches 3, you have f of x to be evaluated times limit as x approaches 3, you have g of x to be evaluated, and you can just multiply these if you have a good right hand and left hand limit. When you look at f of x approaching 3, x approaches 3 from the left, x approaches 3 from the right, left hand, right hand limits. Let's look at that for f of x. F of x is this horizontal line. At all instances, it's a horizontal line. Looking here at 3, you're still getting a 4 on either direction, so the limit here equals a 4 for f of x. For g of x, as x approaches 3, we look as x approaches 3 from the right and x approaches 3 from the left. What are these right hand and left hand limits? You have 3 comma 0 here, and you look up over here, this parabolic curve, and you look across, you see a 9, but you have both right and left hand and right hand limits equaling to one another because it's a continuous function. There's no break or interruption in it, and in both of those instances it ends up being a 9, right hand and left hand limits. So what do you do over here? You multiply them 4 times 9 and you get 36 to be the overall limit of the product of this. So the product of this function over here as x approaches 3 will equal to 36. The individual products multiply to give you that 36. Let's look over here. Limit as x approaches 0, we have this quotient, so we have to evaluate the limit of this quotient, and again you can use the properties of limits, separate them individually across their individual limits, f of x, then divided by limit as x approaches 0, g of x. The only thing you have to establish is that this does not approach or become 0, so you don't zero out the denominator. When you look at the parabolic function, which is g, you're not going to have a 0 because limit as x approaches 0, you'll have a value here of minus 2. But let's look individually. For f of x, we look at the f functions, the left hand and the right hand. As x approaches 0 from the left and as x approaches 0 from the right, these are my left hand, right hand limits for the function. Now here we don't have right and left hand limits equally because there's a break and interruption. As x approaches 0 from the left, we have a value of minus 4. As x approaches 0 from the right, we have a value of positive 4. So in general here, as x approaches 0, the limit does not exist because right hand and left hand limits are not the same. But let's look at g next. As x approaches 0 from the left and as x approaches 0 from the right, we have a clear value over here, and that value is minus 2. So we cannot establish in general that this limit exists, but we can establish that in terms of one-sided limits it does exist. So from the right hand side we can actually do a value over here, and there will be two different answers. There will be a right hand answer and a left hand answer. For the right hand answer, remember it's f of x divided by g of x. So you look over here, right hand, it's a 4 divided by minus 2, and you get a value of minus 2. That's your right hand limit, is a minus 2. From the left hand, and this value here represents for this compound function over here. For the left hand, you're looking at the left hand values. You have a minus 4 for the f of x divided by minus 2, and you get a value of 2, and that's the value over here. So in general, a two-sided limit does not exist. Only a one-sided limit exists, and they're different for each case, and the values have been shown to you. But from a very pure sense of the word, limit for this function will not exist because you don't have a clear right hand and left hand limits equaling to each other. You can only establish separately individual left hand and right hand limits. Limit as x approaches minus 2, we again have a quotient of limits, and there's a constant multiple. You know, based on the constant multiple law, you can just push it out, and you're looking at limit as x approaches minus 2. You have to establish f of x over g of x and develop a value. And here, since you have a quotient, a rational function, you should always see if this function will zero out. And you look across at the g function right here, it ends up being here at an x-intercept. So technically, you know that the limit here will not exist, but because you'll have a 0 in the denominator. But just for the sake of practice, let's just individually establish these. For f of x, when you're looking at x approaches minus 2 from the left, you're looking here at this part, minus 2 from the left, you're getting a value of minus 4. And as x approaches minus 2, we're looking right here at this point, from the left and from the right, you're getting a minus 4. For the g of x, when you look over here at x approaches minus 2 from the left and x approaches minus 2 from the right, let's put it right over here. What do you get? As x approaches minus 2 from the left, we're getting a value here of a 0. You're looking at the y value here, and as x approaches minus 2 from the right, you're getting a value of a 0. You would technically, if you had a good answer here, you'd multiply that good answer by that 2, but it's irrelevant here. You have for both of these functions right hand and left hand limits equal to one another, and in all instances f of x over g of x with regards to this limit as x approaches minus 2 will end up being a minus 4 over 0, which you cannot do, so the limit will not exist. Even let alone a good left hand and right hand or two-sided limit does not exist, but in each case a one-sided limit still does not exist, because one-sided limits are still minus 4 divided by 0 and minus 4 divided by 0, and two-sided limit for sure does not exist. We'll end this video now with this concrete example, and keep in mind always a direct substitution property of limits, where when you're dealing with a polynomial expression or a rational function and the value of a is very well in the domain of that entire function, you can easily substitute and directly substitute this into place. So always keep that little trick handy. Using the laws of limits that we know, the numerator expression will play out the following way. Limit as x approaches minus 2, and then a constant multiple law kicks in over here with the coefficient 2. You can push that aside. Limit as x approaches minus 2, we have an x square, and then finally we have limit as x approaches minus 2, we have this 1. The denominator expression will be handled next. We have limit as x approaches minus 2, we have this 5. Then again we have a constant multiple law coming in here. We can push the 3 out as a coefficient. Limit as x approaches minus 2, we have an x. In all of these instances, we cannot develop a vertical asymptote with this value minus 2 in the denominator. Therefore, it's very safe for us to apply the direct substitution property of limits. You could literally put minus 2 in places of x and calculate them out. When we look at this value here, it becomes a minus 8. Minus 2 cubed is a minus 8. Here we have a minus 2 squared, which is a 4 times that 2 is a plus 8. The limit as x approaches minus 2 for that 1 will just be a 1. Limit as x approaches minus 2 for this is just a 5. Why? Because you could think of this as a horizontal line, y equals 5. At any point on that horizontal line, the output is always equal to 5. Here you have a minus 2 coming in here, multiplying with this minus 3. Minus 2 times minus 3 is a plus 6. You easily do the arithmetic here and you get a minus 1 over 11, and that's the answer of this limit rational function as x approaches minus 2. This question coming right out of my calculus textbook, and the answer is good. So that's all I wanted to present. Keep in mind, all the limit laws are not hard. They're not intimidating by any means. They're actually quite easy, and they allow you to break down complex functions into easier parts that you can manage. Thank you for watching. Have a nice day.